Alright, so this is section 7.3, which is on uncertainties in the least squares coefficients. So let's first recall the true line is yi equals to beta 0 plus beta 1 xi plus epsilon I. And epsilon I is the measurement error. And then we also have our least square line, which is yi equals to beta 0 hat plus beta 1 hat xi plus ei. Ei is the residual. And beta 0 hat and beta 1 hat are used to estimate beta 0 and beta 1. So whenever we talk about estimate, we want to measure the uncertainties of our estimate. So because we want to be able to calculate confidence intervals and doing hypothesis tests on these estimates. So let's first, there's an assumption to do anything. So the assumption in one sentence, we're going to assume epsilon i's are independently normally distributed with the same mean 0 and the same variance. It's called sigma square. So technically, this is a really hard assumption to satisfy. So this is hard to satisfy. For the purpose of practices, from now on we're going to pretend this assumption is satisfied. In reality, there's no way. This is a very strict assumption. But well, without this assumption, we can't do anything. So we're going to assume or pretend this assumption is automatically satisfied. Then we can do uncertainties with beta 0 and beta 1. Okay. So for beta 0 hat and beta 1 hat, beta 0 hat has mean beta 0, which means this is unbiased, and beta 1 hat has mean beta 1. Okay, and I'm gonna throw you a lot of crazy values here. So that's the mean for beta 0 hat and beta 1 hat. Now, the standard deviation of beta 0 hat is this thing. It's sigma times the square root of 1 over n plus x bar squared over the sum of xi minus x bar squared, I from 1 to n. And remember, an easier way to calculate that denominator is this is also equal to xi squared added together and then minus n x bar squared. So that's the standard deviation for beta 0 hat, and sigma beta 1 hat is equal to sigma over the square roots of the sum of xi minus x bar squared, which is equal to sigma over the sum of xi squared minus nx bar squared. Well, it's not over yet because there's a quantity sigma we don't know what it is. So sigma can be estimated using S, which is equal to this even bigger quantity. So this is 1 minus r squared times the sum of yi minus y bar squared over n minus 2. this is equal to, the same principle applies. It's easier to calculate sum of yi squared minus, and then subtract n by y bar squared, n minus 2. Okay, so that's how we estimate the value for the sigma in our quantity. Okay, so we have the mean, we have the standard deviation, and last thing we have to know is that to deal with estimates in beta 0 hat, beta 1 hat, we use the student's t-distribution. And whenever we use the student's t-distribution, we need a degree of freedom. So the degree of freedom is n minus 2. Alright, I'm gonna do an example in the next video.